now. Now I can really hear my voice. I can't talk too loud. It's really loud speaker system. Okay, so I'm starting right at the beginning. Most of my talk is about constant mean curvature surfaces in three manifolds. Some of it's not, but most of it is. And so it kind of starts also with our kind of classical ideas about surfaces and Gauss map. So I'm going to be looking at Gauss map is going to play a fairly important role in the Lie group setting. So I'm going to also have a Gauss map in the Lie group setting. I'm going to use this picture again, this figure. So anyway, we have the trace of the second fundamental form. It, for me, is going to be 2 times too big, so that's going to be, the mean curvature is going to be sort of the average of the normal curvatures, and that's going to be half the trace, okay? And it turns out surfaces of constant mean curvature, so that's where the mean curvature at every point has the same value, these surfaces satisfy a nice variational property that they are critical points to compactly supported variations where the variation preserves volume. And what that means, sort of the algebraic volume. You want to push just as much on one side as you push on the other side. So the integral of somehow the variation function is 0. Is a function on the surface. Okay, so classical examples, we have round sphere that minimizes surface area subject to a volume constraint, so it's certainly an example. And it's easy to see it's homogeneous, so it certainly has constant mean curvature. Also, the cylinder is homogeneous, and then we have our non-homogeneous examples found by Delaunay quite a while back. Anyway, back in the 18th century. So these are surfaces of revolution. So all these are examples of revolution. And if you restrict to the case where the mean curvature is 0, things are, again, a little bit better. You have that the area functional for compactly supported variations is a critical point for any variation at all, for any, say, smooth variation. So we have those kind of things. And again, a famous examples of minimal surfaces are the catenoid and helicoid. And I'm going to be talking about these particular examples a little bit more later. Okay, so that's our situation. So we have soap films on wires are least energy, and least energy in this dimension implies least area. So we parameterize it conformally, we have least energy. So that's a physical property of being a soap film. And for a soap bubble is somehow you have pressure that's different on each side, but you maybe have a stable configuration. So we have examples. Soap bubble is a big example. Even if you blew that with a different shaped wire, not a circular wire, you're going to get something that looks kind of like a sphere, but it's not going to be exactly a sphere. Okay, so that's kind of things we have. Non-zero constant mean curvature. And the first couple of slides are about an invariant that plays an important role in the first theorem that we're going to be talking about. And that's an invariant which is mysterious and unknown. That's called the critical mean curvature. Okay, that's actually this second definition. So h of m is somehow an infimum on the mean curvature function over immersed closed surfaces inside the space. It's not a minimax. It's some kind of strange thing. It's a way of getting a number. It turns out it's important. You can think of surfaces of a constant mean curvature, then this absolute value is just the constant mean curvature. So it's kind of looking for sort of an infimum of those mean curvatures. It's closely related to this constant, which is more familiar and easier to calculate. That's the Cheeger constant. And for me, I'm really only going to, that's not quite true. For me, the way I've defined it, the Cheeger constant would be 0 for any closed Riemannian manifold. So this is not quite the usual definition in that setting, but I'm going to just take this because it works for me. So it would be 0 in these other settings. Usually defined this way for manifolds with infinite volume. Okay. All right. So then we have this, at least in homogeneous 3 manifolds. That's the first part of my talk. I'm talking about homogeneous 3 manifolds. So Riemannian metric, you have transitive symmetry group. So when that manifold is simply connected, I can relate this sort of strangely defined number, it's hard to understand, to a number. In certain cases, I can calculate it very easily. There are other cases I don't know how to calculate it so easily, but in a large number of cases, I can certainly calculate this number up here, defined up here. And so it just helps us do that, and also gives us insight into solving isoperimetric problems in the non-compact setting. Okay, so think of like R3 with a homogeneous metric. So you have a three-dimensional family of metrics on R3 that are homogeneous, and they have all relatively different kinds of properties. But anyway, one proves this theorem by studying what are called H of Y foliations. So somehow you create foliations of the space that end up having the critical mean curvature as their mean curvature. And then it's somewhat delicate. One of the parts is a studying of what's the geometry of isoperimetric domains. So you fix a volume, think of it as a big volume. Can I say something about the geometry of when I solve the isoperimetric problem in this R3 with a homogeneous metric? And you can say some things. You can say, for example, that the mean curvature of the boundary of such domains are always bigger than the critical mean curvature. That kind of falls from up here. But anyway, but it was very nice is the mean curvature of the boundaries, as the volumes go to infinity, actually converge to the critical mean curvature. And there's some other interesting things we also proved, like the radius of these domains, the inner radius as Riemannian manifolds with boundaries of isoperimetric solutions, the isoperimetric problem, also go to infinity. So they get kind of big. That's certainly believable, but maybe not so easy to prove. Okay, so we're getting to the first real theorem of my talk, and it's one of the ones I'm actually going to spend some time going over the proof. The proof is really beautiful. It's one of those things that you can appreciate it, okay? And some part of it's already on the archive, so you can find some things about it, these certain manifolds. Okay, so first of all, to understand the problem I'm talking about, it's called the Hopf uniqueness problem. One needs to understand a basic property about simply connected homogeneous three manifolds, and that's that they're usually metric Lie groups. That means a Lie group with a left invariant metric. Okay? So that's when I say metric Lie group, that's what I mean. But there's one big counterexample, and that's a round two-sphere cross R. You take a sort of product of a sphere, or a nice sphere, a round sphere, a homogeneous sphere with R. Those are the examples which are not, do not have a Lie group structure. And the metric has come from a left invariant metric. Okay, so this next theorem completely characterizes constant mean curvature spheres in homogeneous manifolds in general. So I should say one more thing up here. So M, and what's coming up, M is going to be a homogeneous Riemannian three manifold, and X is going to denote its universal cover. So right, you see a purple X, that's the universal cover of your general homogeneous manifold. So the first theorem says, if you have two spheres in your homogeneous space, and they have the same mean curvature, then they're congruent. There's an isometry of the space that takes one to the other one. Okay? So that's very nice generalization of some previous results. And a complete characterization of at least how many do you have? At least if you have, can you have more than one? The answer is somehow no, up to translations or congruences. And then you'd like to say, what are the values where you obtain constant mean curvature spheres? That's the sort of the existence part. So the first part is a uniqueness, and the second part is uniqueness. It says, if you're not diffeomorphic, if the universal cover is not diffeomorphic to R3, then you have an example for every possible mean curvature. And notice that I said two spheres have the same absolute mean curvature. That's a question of orientation. You can change the normal field, you change the sign of the mean curvature. So it's really the absolute mean curvature. Here I'm thinking more any number, possibly negative. Okay, and if you're R3, then there's some kind of subtle obstructions. And the obstruction is somehow characterized in terms of the Cheeger constant of the space. So the absolute mean curvature must be bigger than the Cheeger constant divided by 2. And if you remember from a previous page, that's the critical mean curvature. So think of the critical mean curvature as that number. Or if you want to calculate it, that's easier to do. Usually it's fairly easy to calculate this number. Okay, so that's sort of the main uniqueness theorem. And then there's a theorem that tells you some other nice properties you'd like to know. And about somehow the stability operator, geometric aspects of these solutions. Okay? So if you're minimal, so S is going to be my, throughout this theorem, S is going to be my constant mean curvature sphere. So remember, H is some real number here. Constant mean curvature sphere. If that sphere is minimal, and if the universal cover is S2 cross R, S2 meaning constant curvature metric on the sphere. So you think also topologically here, okay? Then the original surface is totally geodesic. It's just like one of the factors in the product description. And stable has nullity 1 for its Jacobi operator. So the next statement is the otherwise statement. Suppose I'm not in this very easy to understand case. Totally geodesic and S2 cross R. What if I'm not in that case? What can I say about properties of the surface? And there's sort of 2 or 3 key properties. First of all, the surface has index 1. So that might make you think, well, these are all solutions to the isoparametric problem in that manifold. I mean, maybe they're weakly stable, things like that. And generally, they aren't weakly stable. So you can lower the second order, you can lower area and preserve volume. So that's not true. But anyway, it might make you think that it was true. So index 1, still a nice property, and nullity 3. So you have all these motions in the space, and they give rise to Jacobi fields, right? You have a three-dimensional space, you move things around. There are no non-zero vector fields on a sphere. Anyway, you get a nice kernel. So the kernel, three-dimensional there. So we have that. And the geometric property is that all the spheres also bound balls on their mean convex side, even when they're not embedded. So sometimes they are embedded. They still bound a ball on their mean convex side, an immersed ball. Okay, so that's some nice properties. And this is one of the key ideas of uniqueness in these spaces. There should be associated to the sphere a point. When it's totally geodesic and S2 cross R, that point's not very clear. But when you have this ball, somehow that bounds the sphere, maybe there's somehow a center and it's somehow uniquely defined. And that's the case. There's a point associated to M called the center of symmetry of the surface, of the sphere. And every isometry of that ambient space that fixes that point also leaves invariant your sphere. So it's maximally symmetric, which you would maybe expect to happen if you have uniqueness. Okay. All right, so where does this theorem come from? So I'm going to tell you what motivates this theorem. Where did the proof come from? Where the ideas come from? Certainly, the main idea goes back to Hopf, a main idea. He proved that in R3, the simplest setting, round spheres are the only constant mean curvature spheres. And then there's just certainly 1 up to congruence for every radius of the sphere. Okay? Then you have a sort of a really nice improvement on that work of Hopf back in, well, that's probably earlier than that, but anyway, in 2000, it says 2004, it's probably the day of the journal article. If you have a 4-dimensional isometry group, then you might expect your spheres, this goes also back to some questions asked by Sheng. I should have said that. But anyway, if you have a 4-dimensional isometry group, you might expect that your sphere is a surface of revolution. So if the ambient space has lots of symmetries, then maybe your sphere also has this symmetry. And then you could somehow describe these spheres by some curve, satisfying some ODE. So anyway, that's what happens. And from that classification of ODEs and what the curves are, you can prove that they are uniquely defined by their mean curvature. Okay, so that's certainly a key thing. Then we sort of go forward quite a few years. Probably this was around 2010 when we figured out these things, but it took a while for these various papers to get accepted. So a big sort of leap forward was an example where we studied Sol. So Sol is a Lie group, and it has a left invariant metric. And here's the sort of the Thurston view of what that metric is. It turns out there are lots of other metrics. This is not the only left invariant metric on Sol. And so even though we proved this theorem, uniqueness, and some nice results about spheres in here, we didn't know this theorem for other left invariant metrics. There are other left invariant metrics on Sol, less symmetric ones, and for those we didn't know the theorem. So what is this theorem? You take this particular metric on R3, then you know that the spheres are unique, embedded, and have index 1. Furthermore, if you're willing to translate them so they're center of mass or center of symmetries at the origin, then they have all these other symmetries. The vertical planes of symmetry, they have these two vertical planes, the XZ and the YZ planes are planes of symmetry of that metric. And you also have some diagonal lines along which you can rotate by 180 degrees. So you have, and those are somehow the ambient symmetries. Okay? And to say something about here, these guys proved a substantial result, but they couldn't prove it for all mean curvatures. For all mean curvatures, one needed to get what call area estimates. One needed to prove that Sol has Cheeger constant 0. Okay, just for you to know. Sol has it's a unimodular Lie group, so its Cheeger constant is going to be 0 anyway. So it's 0, and what they knew is if the mean curvature was reasonably big, then they knew the result. But as the mean curvature got closer to 0, you have problems of knowing if you have area estimates. Are all, say, spheres constant mean curvature with area with mean curvature bigger than a half? Do you have a bound on their areas? So there are these kinds of questions, and with some luck, I was managed to figure out those area estimates. So as long as I'm somehow away from the Cheeger constant, away from 0, I could find these estimates and therefore complete their argument to all mean curvatures. And that still is kind of somehow the hard part, these area estimates of this other theorem. So here's a rephrasing of that theorem. Okay, so this is, I'm just going to think of the simply connected case, okay, three-dimensional homogeneous. I'm not going to look at this case. This case, think of it, four-dimensional symmetry group, completely understood. You can explicitly write down all the constant mean curvature spheres. We're not looking at this case. That means we're looking at the case where X has a Lie group structure, and I'm going to use that really strongly in the proof. That group structure plays a very important role in understanding the proof of this theorem. It gives you makes it very clear instead of muddy. So what are the situations? We're diffeomorphic to S3. Well, the three-dimensional family of metrics there. And for each of those metrics, you have a constant mean curvature sphere for any value of the real numbers, for any real number. If you're diffeomorphic to R3, notice I replaced Cheeger constant by the critical mean curvature. That's somehow the more natural number to look at in this problem. And in the case of S3, you also know that you have a uniform bound on there's So if you look at all constant mean curvature spheres in SU2 with a left invariant metric, then there's a uniform bound. There's a sphere which is biggest. It's not always the minimal one. Sometimes it's not the minimal one. All right, so, and the other key property is this sort of bounding a ball on the mean convex side, index 1 and nullity 3. Okay, so like I said, we're really looking at this theorem in the setting where X has a Lie group structure. Okay? Now, you might even have a one-parameter family of Lie group structures. So I'm going to pick ahead of time for the proof, I'm going to pick one of these Lie group structures. Okay? And I'm going to fix it. Yeah. For example, a hyperbolic space has lots of Lie group structures, so it's as a Riemannian manifold, it's a left invariant metric on a whole one-parameter family of different Lie groups. So we're going to fix that Lie group structure, and that comes back to my first picture. Remember, we have the Gauss map. We can take a normal vector, a unit normal on the surface. We can left translate it to the origin in our space. The identity element is now going to play the role of our origin, and it gives me a point in the unit sphere at the tangent space at the identity element. Okay? That's going to be my Gauss map. Okay? And it's called the left invariant Gauss map. And just say a couple of things about it. A real key result is that we can completely characterize constant mean curvature surfaces in terms of a Weierstrass representation and its Gauss map. So if you have some kind of a disk in the plane, a unit, say the unit disk, and you're looking at maps into the two-sphere, and you can stereographically project it onto the complex plane, say from the south pole, then it turns out that to be a constant mean curvature surface just means it satisfies some conformal second-order PDE. Okay? And sort of like necessary and sufficient conditions. And furthermore, you get this map into the Lie group, and it's well-defined up to left translation. So there are some minor restrictions in certain values of the mean curvature and the image of the Gauss map. But anyway, I'm going to skip that. But most of the time, this is basically what I'm telling you. There's a Weierstrass representation that somehow is defined up to left translation. Okay, so how does this proof work? It's a moduli space argument. Okay, so we're going to create a moduli space, and remember the theorem says there's one surface for every mean curvature. So I got to make my moduli space match up with it. So I'm going to see a curve. And I start with something I understand better. Sigma is a fixed H0 surface in X of index 1. Okay? Those exist, for example, take a teeny volume, solve the isoperimetric problem. You can see you have a little sphere, a little teeny, almost round sphere, and that little almost round sphere has index 1. Okay? So these things exist. There's at least one, but I'm going to fix it for a while. I'm going to fix it for a while before I look at any kind of other spheres. I'm going to fix this one of index 1. Okay? So the first thing you note is the stability operator is a Schrodinger operator on this surface, and it has at most nullity 3. In fact, it has exactly nullity 3 because I can move the sphere around, and there are no non-zero vector fields. So anyway. So I have nullity exactly 3, okay? You can't have bigger than 3. And that's going to help us during a deformation process. So eigenvalues can't cross 0 somehow. The ones that are 0 are coming from the right invariant vector fields on the Lie group. So anyway, it kind of helps us understand things. This is, so I'm going to work with this moduli space. Non-congruent index 1 spheres. Okay, so remember index 1, I'm not looking at all spheres, I'm just looking at these. Then that's an analytic one-dimensional manifold. So if I take a given sphere, since it has index 1, nullity 3, I can apply the implicit function theorem, so there's a curve of spheres nearby it that have changing mean curvature. It's a one-parameter family, and that gives me my one manifold. It's pretty easy to do because the nullity is 3. You can kill all the motions. You can somehow get rid of it. It's like being non-degenerate. Okay, so that's just the implicit function. That's pretty straightforward. The next step is surprisingly tricky to do. It says you now look at this left invariant Gauss map. Okay, so you have your sphere of index 1. You have a map to the two-sphere. And it is a diffeomorphism. So that's how it's kind of interesting. It's certainly true in R3, right? If you think in R3, it's a identity map, kind of like, right? You take a sphere, it's kind of identify it with identity map. Anyway, and this is, like I said, somehow surprisingly tricky. If you asked me to write down the proof of this, I would have trouble. I would have to go back to the paper and kind of look it up. But anyway, it's a nodal, the idea is kind of reasonable, and it uses a nodal domain argument, something in the kernel of the derivative map. Basically, it's sufficient to show it's a local diffeomorphism, right? Because it's simply connected. So, and then you use that representation theorem I was talking about before to get some kind of contact with some other surface, and anyway. But that's step 2. And once you have step 2, you immediately get curvature estimates. Because when you rescale points of big curvature, curvature estimates as long as the mean curvature is bounded from above, all right? Certainly, there are no curvature estimates on little teeny round spheres, but think of bounding the mean curvature from above, you have curvature estimates. And that's easy to see, because when you rescale, I can produce minimal surfaces in R3 that are not flat. And what's the degree of their Gauss map? Negative. They have negative degree. They're negative Gaussian curvature. So that's just kind of trivial to get curvature estimates. Okay, this is the really hard part of the theorem, and I'm going to try to, I think I'm going to be able to do it, give you a pretty good idea of how that works in the 3-sphere. So there are 2 kinds of area estimate. What does it mean to be an area estimate? Well, this is the easiest case. If you're topologically the 3-sphere, or the group is SU2, that means there's a global estimate. Areas of all spheres are bounded. There's a biggest value, if you want, kind of like that. Okay, so that's what we understand what that means. What's not so clear is what it means when you're not SU2. So not SU2 means topologically R3. And think about what happens in R3 with a flat metric. What happens to the area of spheres? Well, they go to infinity. As the mean curvature goes to 0, which is 1 over the radius of the sphere, then you have this property that you don't get area estimates, but as long as I'm willing to back away by any amount from the critical mean curvature, right, any positive amount, then I have area estimates. It's only when I approach this critical mean curvature that the area goes to infinity. And that's actually what happens. The areas always go to infinity, but you need this estimate to try to do compactness arguments, to try to understand what this family is. So once I have that, oh, I should have said one more thing. That previous theorem I talked about showing the critical mean curvature is twice half the Cheeger constant. That theorem, already it's not hard to see that there are no spheres with critical mean curvature when you're topologically R3. So anyway, that's, if you went back and saw that, it's really easy to understand. Okay, so step 5. So once we have curvature estimates and we have area estimates, then we can understand this whole family. You have this original surface sigma, it's in a one-dimensional family, and because we have, anyway, it's not hard to see that, in fact, this whole space, this whole thing is an interval. Now here I'm stopping at 0. I'm thinking if I go to negative mean curvature, then I'm just going to block it off. So anyway, anyway, so we can think of those as intervals, okay? Okay, right, so this modular space is going to be an interval. If it's SU2, it's the whole interval. Otherwise, it's an open interval. That just follows more or less immediately from the curvature estimates and the area estimates. Okay? And the fact that it's a one manifold, you can always go a little further if you're ever at one of these examples. Okay, so how do we get uniqueness? How do we go from these one manifold of index 1 examples to all examples? Well, if you have another example, it's a sphere. It has its less invariant Gauss map. And now I know that I also have an index 1 sphere with the same value of the mean curvature. Say, let's just fix sigma. Okay, suppose you have another sphere which is different from the same mean curvature. Okay, then you could try to say, well, the Gauss map of the original sphere, sigma, was a diffeomorphism. I can And I can kind of compare second fundamental forms at corresponding points where they have the same normal vector. Okay? And by being clever and using the representation theorem, from that you can create a non-zero complex quadratic differential which has isolated negative zeros if this surface is not a left translation of sigma. Remember, the representation is all in terms of uniqueness up to left translation. The Gauss map somehow determines everything. Okay, so anyway, anyway, that's certainly believable, and that's what you do. And because the order character of the sphere is positive, we can't have such complex valued differentials that have isolated zeros of negative index. Okay, so for topological reasons, that means this m here must have been sigma, up to left translation. Okay, so now we finished the whole proof. You just have to kind of put things together. So the space of these things is equal to that, and because we have one for every possible mean curvature, and then you understand the theorem, okay, in terms of the possible values of the mean curvature. Each H-sphere in the space has index 1 and nullity 3. And finally, we have this ball. When the mean curvature is really big, you have almost a little round sphere. It's almost round, bounds a ball. Then as the mean curvature goes through this family, you can watch this sphere, this ball, move. Even if the surface crosses itself, you can watch it, and it's easy to see that it just continues being there as an immersed submanifold. So that's pretty easy. You do use the maximum principle, or the mean curvature comparison principle, but and finally, right, then we also see we have an area estimate. So that finishes the proof of the theorem modulo the area estimates, which are quite long and difficult. The case of SU2, I'm going to explain a slightly different proof than is in the archive paper. It needs some results from the second paper. There's a proof there of the SU2 case, okay? But I'm just going to say I know a little bit more. I'm going to make the proof easier. So let me just go through this proof. So you want to prove you have uniform area estimates. If you, I know that's true if I have big mean curvature. The question is what happens to the areas I come near some problem. I start with this family and I come down mean curvature. So I can create a sequence of surfaces, HN, varying, of examples in here, and their areas go to infinity, okay? But they have bounded mean curvature, okay? They have bounded curvature as well, okay? So they kind of want to converge, except the area is going off to infinity. All right, so by picking a base point cleverly, okay, so I'm going to pick this. The area is going to infinity, and I have index 1. That means it's kind of easy for big domains to be stable. So I can pick those domains, pick a base point in those domains. And I also have the area of the Gauss map is 4 pi. Remember the Gauss map of the surface is 4 pi. It's a diffeomorphism. So I can also pick those points on big stable regions so that the differential of the Gauss map is really small. Otherwise, I'd have too much area. So you sort of uniformly small. And what happens, that those subsequences are going to converge to my limit surface, which has a completely degenerate Gauss map. Degenerate in the sense it has rank 1 at every point. And that, you can prove it doesn't have rank 0. But anyway, it's rank 1. So the image looks like a curve on the sphere, an immersed curve. But you study that a little bit more in like a second paper, and you can prove that degenerate Gauss map means that you're actually invariant under a right invariant vector field. Okay? It's invariant under an S1 action. You're in SU2, you're invariant under an S1 action on the sphere. So that means that the image is like a cylinder. And in fact, by being a little more careful, you can see that it's a torus. Okay, that's a little more subtle. It's a little deeper fact, and you can see that by seeing that the image of the Gauss map is actually a smooth closed curve on the sphere, and then you do a little bit more analyzing. So the image is actually an immersed torus. So and it's stable. So now it's not hard to show that that's a contradiction because You take any point on it, you look at another right invariant vector field that's, remember, we have a right invariant vector field that's tangent to it. That's k. This is another one. So I pick in a different direction in the tangent space of that point, another right invariant vector field. And I inner product it with the, be a different right invariant vector field. It's linearly independent. So it's a different vector at that point. And now you create this Jacobi function, which is a standard thing. The Kelling field and a product of the normal, and I get a Jacobi function which changes sign. And that's a contradiction because we said the surface was stable. Let me just say why is it not, this is changes sign, because if it didn't, you would have two right invariant vector fields tangent to the surface. That means it's a subgroup. And there are no two-dimensional subgroups in SU2. So anyway, so that's the proof. Okay, so now I'm going to change topic a little bit. I don't know how far I'm going to get. I got a lot of things I wanted to talk about. We'll see how far I get today. But this is another sort of one of these big projects I've been working on. So I've been working on that last project, I'd say, certainly 7 or 8 years. It's been a while. With other people, of course. So this is a project I've been working on about 10 years with Giuseppe Tenaglia. And the question that motivated our interest in what we end up doing is classification question. Can I put a plane into R3 as a complete embedded surface, so it's simply connected, and such that it has constant mean curvature, which is positive? I can certainly put a plane in space, and I can put a helicoid in space, but those have 0 mean curvature. Can I put a plane into space with positive mean curvature? This is the problem I've been working on for 35 years, probably. I think, is it 35? Anyway, it's been a long time. So here's our example that's not simply connected. Here's like an immersion of the plane, conformal immersion of the plane into space, but it's not embedding, constant mean curvature. So the answer is yes, or no, depends on your point of view. The only simply connected constant mean curvature embedded surfaces, non-zero constant mean curvature, are round spheres. There are no planes. You can't put planes into space in a complete injective way. Okay? And like I said, I've been interested in this problem a long time. This is when I originally was proving things about this. I remember talking to Rick and Yao and Berkeley. I think was it that year? Anyway, we were talking about this problem. They were curious about it. Okay, so let me tell you a little bit more closely related result, which I need for doing some other things. A few years ago, with work with me and Harold Rosenberg, based on work with Colby Minicozy and some other work with them, if you ask this question for minimal surfaces, take a plane, put it into R3, complete, minimal, and injectively embedded, is it what you think it is? Is it a helicoid or a plane? And the answer to that is yes. Okay? So these are the only two examples. So that means we now have a complete characterization of simply connected, complete, and embedded in R3, constant mean curvature. Okay, so let me tell you a little bit more about things along this line that are more general. Okay, so this is, I'm going to talk about this in a little bit, what the Claude-Yao problem was. So I'm looking at a surface in R3, complete, connected, embedded, an H surface, constant mean curvature H, could be minimal. Okay? If it has positive injectivity radius, then it's properly embedded. Okay? But how do I know a plane with constant mean curvature has positive injectivity radius? I mean, there are all these questions that kind of come up. If you have finite topology, a really crucial thing is you end up proving it has positive injectivity radius. Therefore, it's properly embedded. Therefore, I understand there are no planes with embedded in R3 with constant mean curvature. And go back to 1986. And here's a very interesting characterization of having bounded second fundamental form. Very, very simple. It says bounded second fundamental form, and now I'm assuming H is positive, is equivalent to having positive injectivity radius. So sort of a topological property of it looks like a disk actually means it has bounded second fundamental form. So try to understand this. Okay, so this theorem certainly related to some previous results. H equals 0. The first two items were proved by Harold Rosenberg and myself. And, but our work was certainly based and was in a manifold setting, which we also want to generalize some of these things, but certainly based on crucial techniques in their paper, in the last paper they had, last paper on this subject in the Annals. So finite topology, minimal, complete and embedded, then it's always proper, okay? And what's interesting is there's remnants. This thing somehow continues to hold in manifolds with bounded geometry, like a closed Riemannian manifold, Riemannian 3 manifold. So you have to kind of understand that. But very important, the ejectivity radius is positive. Okay? Right. So, okay. So I'm going to give again an indication again. How do we understand the proof of this theorem? And probably the neatest way to think about it is this particular theorem, and I'm going to tell you some other things that seem more general still. You take an embedded disk, say, of constant mean curvature 1 in R3. Constant mean curvature and a compact disk. Constant mean curvature. It could be really huge. I can take connected sums of these things. It could be almost going all the way to infinity. But it could be like huge, but it's still topologically a disk. It has a radius. There's a constant mean curvature 1 disk. No point on the disk can be very far from the boundary. It's similar to kind of it's a feeling of it like for stable minimal surfaces. Some of it's really curvy. Anyway, some kind of feeling about it's behaving like somehow it's stable. Okay, and in particular, you immediately get you don't have any complete simply connected surfaces with non-zero constant mean curvature, because why? Because every topological Riemannian plane is a union of disks. You can expand it. It's topologically just the usual plane. So the radius of those disks has to go to infinity if it's an exhaustion. So anyway, that's pretty easy. Here's the fundamental result. So you say, where did all this come from? Where do all these other results come from? They come from this theorem, okay? So I'm going to state it in the case of complete, locally homogeneous 3 manifolds, okay? Okay, it says you pick a positive number. So this is picked out ahead of time. And then there's some kind of universal constant related to that number, so that for all H, of course, you're also related to the manifold. H is bigger than or equal to this. Those are the mean curvatures I'm going to look at. So at least, say, 1/2, or at least 1/10. Some number, at least 1/10. Then I have a bound in the second fundamental form once I go away from the boundary. So again, this is kind of like saying it's behaving like stable minimal surfaces, except the relationship is not as nice as one has for stable minimal surfaces. It says it's once I'm at least some distance from the boundary, I have a uniform estimate for those disks. And I don't know if you can see it, but this theorem immediately gives that radius estimate. The very strange thing here is the mean curvature is at least as big as this. So if you think about that a little bit, that means once the mean curvature is really big, the surface is compact. It has a bound on the radius, if you just think about that. Anyway, so this really has inside, even though you don't see it, radius estimates in it. Okay, at least it's a long proof, and it's long and it's a hard proof, so I'm not going to talk too much about the proof. I'll just say one of the results along the way is you try to generalize a lot of the techniques are based on things that Coleman and Cozy did. In particular, you want to generalize their one-sided curvature estimate for embedded minimal disks, okay? And this gives a complete generalization for any mean curvature. Somehow there's a scaling here. So the picture is that you have the boundary. Think of the boundary as outside of a ball of radius r. And then when you comes in, and it doesn't maybe intersect this plane here. Anyway, this picture is correct, but it's more general than I just said. Here the boundary could be actually underneath there. Then it's graphical. It looks graphical when you get near the origin. And there's a uniform estimate. So there's a constant, and this, anyway. So when you get close to a plane or close to another surface that has bounded second prime F-form, it also controls the norm of the second prime F-form. Okay, so now switching directions again a little bit, trying to understand this Calabi-Yau question. And it's one of my favorite problems. This is a problem, I'm guessing, probably in about 10 years, I will actually try to really completely solve. So what is this problem? First of all, there's this interesting picture I drew here. It's a solid infinite hole donut compact. So there are all these holes in it. Think of it as white part solid. And these sort of holes are limiting to a point over here. So we're talking about infinite genus. But it's a very specific surface. It's a very specific domain. It's this domain. Then I claim this domain has an amazing property. Take any open surface, so say connected, just to make it easier to understand, an open connected surface, and suppose that every end has infinite genus. Okay? Like a triply periodic minimal surface has one end, infinite genus. That would work. Or take any non-orientable surface such that every end of it is non-orientable. That would also work. So you can have examples with an uncountable number of ends. You think of really complicated surfaces. But the claim is every one of them will embed in here as a minimal surface, not just embed, but properly embed. It will properly embed in this open domain. And if it embeds in here, it's equivalent to embedding in as a bounded, complete embedded immersion. Necessary and sufficient. So there are two beautiful parts of this. One is the existence, and one is to say you can't do it if an N has finite genus. In particular, if the surface has finite genus, you cannot put it into R3 in a bounded way. It's a complete embedded minimal surface. So anyway, this is, I would say, this is a theorem that this is true. It's just a question of lots of work. And I'm working on both parts of this. So off and on as the years go by. Okay, so here's where we get more insight, and this is related to, well, definitely not going to finish many of my things. Okay, so conjecture is that look at a surface in R3, complete and embedded in R3 with constant mean curvature. Okay? Suppose it somehow satisfies a reasonable topological condition, otherwise the thing's false, that in balls of, say, radius 1, there's a bound. Any ball of radius 1, the surface has a bound on its genus. Okay? And I'm going to assume initially, say it had constant mean curvature 1. There's sort of 1 and there's 0. There's kind of two cases. Then I claim it has cubical area growth. In particular, it's proper. And I'd say we were kind of close to, if you assume it's proper, I think that we can actually prove this. And you might think, that's an awfully hard to believe conjecture, but if you say proper and you start thinking of the behavior of constant mean curvature surfaces, then it starts sounding kind of actually believable. Yeah, I can almost believe it's true. Anyway, I'm pretty sure it's true, and for proper, I think we might be able to prove it. When it's minimal case, let's just say, I don't know if it's still true in that generality, but let's assume the whole surface has finite genus. Okay. And then there's some special cases where we know this kind of conjecture. First of all, if you have a properly embedded minimal surface in R3, any properly embedded minimal surface, then it's a theorem of me with Rosenberg and Cullen and Kussner that you can't have more than two limit ends. Okay? All right. And this is kind of sort of almost like trying to do a converse. I'd like to say complete embedded minimal, 0 means minimal surface finite genus, that it's proper. I know that if I have a countable number of ends. Notice, if you're proper, you automatically have a countable number of ends because you only have two limit ends. So that you always have a countable number of ends by this other theorem. So anyway, that should be on the archive again pretty soon. So. Okay, so now I'm going to talk about a classification result, partly because it's very important as a tool. So lots of these theorems, we say, oh, that's pretty cool, that's a neat theorem, but classified all these things. What's it good for? They're good for tools. They're good for understanding everything. If you're trying to understand things in at least a 3-manifold, understanding what happens in R3 is important. And it really plays an important role. So this is what's called, I'm trying to understand genus 0 surface. So you can start with a catenoid. I think it's a soap film. I just move the circles sideways a little bit. An amazing fact proved by Schiffman is that this surface is still foliated by circles in horizontal planes. Okay? And then if I bring the curves down, so I go sideways and then I just bring it straight down, I get a 1-parameter family of which they are part of complete, properly embedded examples found by Riemann. So if you do this and then come down, it turns out I get a whole lot of surfaces. So just shift it a little bit. That's an analytic property being circles, and the circles actually in finite time become straight lines, and then I can do Schwartz reflection by rotating around these lines and continuing the surface, and I get a singly periodic surface. Okay? And here's a beautiful picture done by Matthias Weber of part of the interesting part of that surface. It kind of, you can see it kind of looks like catenoids, and they're stacked, and they're foliated by circles and straight lines. Okay, and he defined these in terms of Weierstrass P function on rectangular elliptic curves. And if you're familiar with the Weierstrass representation, the differential is just dz. It's really simple. So here's a better picture from the point of view of geometry. What do these things really look like? I mean, that was beautiful, but this is how they behave. They look like a stack of planes, and along a diagonal line, you glue in somehow catenoids. You kind of do some kind of surgery and connect the planes up. Okay? That's what they look like. And then you need to understand what the topology are. They're an infinite cylinder with points removed, a periodic set of points. And that means the surface is genus 0 and has 2 limit ends. And actually, the conformal compactification is this picture. It's a sphere minus some discrete set of points with 2 limit points. And here's the classification. Proper genus 0 examples, minimal in R3, well, you have the catenoid, you have the helicoid, and somehow between them, you have these examples of Riemann. So the moduli space is naturally a compact interval. Somehow those are all, I'm not worried about scalings and rotations and stuff. The moduli space is this interval. And so notice that the Riemann examples are converging to the helicoid, and that's important. That's important for doing a lot of things. This kind of picture comes back in 1996 when let's see, some of these people, Ross, Perez, and myself, we proved that singly periodic examples were, in fact, Riemanns. And part of the proof was, in fact, understanding this picture. So this picture is a family of Riemann examples which are converging to the helicoid, when in reality they converge to 2 helicoids and a foliation of R3. So, and the singular set of convergence are 2 lines perpendicular to that foliation. So that's important for doing other things. Okay. I think I'll be able to just get to the, I'll get a little way through my shot time. I don't remember when I started. I think a couple minutes late. Okay, so this is about area estimates again. So I'm interested in triply periodic minimal surfaces. And these things come up in nature. People study these. There are actually conferences about these kinds of surfaces. And sometimes they allow themselves to study constant mean curvature ones. Well, it turns out if you, for example, genus 3 examples, every flat 3 torus has an infinite number of genus 3 minimal surfaces in them, embedded. And in fact, the areas go to infinity. You can find a sequence of the area go to infinity. That somehow follows from my thesis, but Trazé did it for all genus. For genus 1, of course, it's easy, flat 2 tori. But genus 2, there are no examples. So once you get bigger than 2, 3 and above, you have sequences of example in every flat 3 torus that the area is going to infinity, and they're embedded. Okay. So the next theorem contrasts that result. So it says if you look for positive mean curvature for every genus, you have an estimate on the area. Okay? And here's a beautiful picture, some triply periodic examples. They're all non-zero mean curvature. You can also put a plane, sort of doubly periodic ones in 3 tori. You can have things that look like this. So this will be my last slide. I'm sorry. Okay, so we have this old result of, well, you can see that, read the names off. I think one person here is in the audience is one on there. And they study minimal surfaces, closed minimal surfaces, and manifolds of, say, positive Ricci curvature. Okay? So closed. We think of this is really bigger than 0, bigger than some number. Okay, so then it's a result of these two guys that the areas of closed, connected, well, they're always connected, but anyway, embedded minimal surfaces of fixed genus in that are bounded. You have a bound on the area, just like I did in the 3 torus. Kind of the same thing, except 3 torus, I was interested about constant mean curvature, not 0. Okay? And then from that, these two guys here, they end up proving the space is compact. That means they obtained curvature estimates. So area estimates, curvature estimates, and somehow a non-collapsing property is not allowed because you don't have any stable minimal surfaces. Anyway, they proved that you have compactness of the space. So the next theorem is trying to understand everything that happens in 3 manifolds. Take a closed 3 manifold. Initially, I'm going to assume the second homology group is non-zero. Why? Because if I have an embedded surface in a homology 3-sphere, then it separates. It bounds a region. And so in this case, if you bound the mean curvature in a range, then you fix the genus, you bound the areas. And you can do the theorem in general. You can look at any closed Riemannian 3 manifold, and you can look at surfaces that are called strongly Alexandrov embedded. Then if you bound the genus, that space is compact. So you don't have curvature estimates, but you can still completely understand what happens when the curvature blows up. And you get these what are called strongly Alexandrov things. And you can sort of bound the number of singular points that can happen in the limits and stuff like that. You can completely understand it. You can understand properties about the index of these surfaces. And I really should stop, I guess. Thank you. Thank you. There were more things I was going to say, but that's it. Spheres, custom mean curvature spheres, yeah.
And you said the area is, so the area is like a function of the mean curvature, I guess?
Yeah, you can think of it, right. If you're not, it's, the conjectures, okay, so if you're in SU2, in general, the area starts out really small, gets bigger, and depending upon the metric, it might then go down again. So the minimal sphere might be even like kind of like a local minimum in terms of area. So this area function isn't monotonic in general for SU2.
Other questions? Okay, you've done that. Thank you.
Okay, thank you.